We're now going to turn our attention to the ParallelFlux class. We've talked about this very briefly in the introductory part of the course, but now we're going to talk about it in more detail. And this will be important because you'll have to implement ParallelFlux or use ParallelFlux in one of the upcoming assignments. So we're going to start by discussing what a ParallelFlux provides in terms of its capabilities. And we'll also describe how it can be used to simplify parallel processing when compared to the flatMap concurrency idiom. So if you recall, we've been showing lots of examples of the flatMap concurrency idiom in various places. And that looks kind of like this thing on the right, at the upper right-hand part of the screen, which is complex and idiomatic. And in contrast, the ParallelFlux is designed to be simpler syntactically. There's a little bit of ceremony involved here, but it actually works quite a bit like the parallel streams that we come to know and love from modern Java. So we know about the flatMap concurrency idiom, which works. It's efficient, but it's also a bit convoluted. So the way you do it is you have flatMap, and then inside of flatMap, you have these inner publishers that are going to be publishing events, and they're going to be running on other threads of control. So you can see here, we're going to have flatMap, and then we're going to subscribe on the processing of the monos within here, and that is just a bit more syntax than we might want. In contrast, look at how simple things are for parallel streams. If you want to do the same function you see here with the flatMap concurrency idiom with parallel streams, much less ceremony is involved. You just take the big fraction array, you make it a stream, you make it a parallel stream, you call map, you call reduce, you're done. Very simple, very straightforward, very streamlined. To get something similar to that in the context of reactive programming with Project Reactor, they define ParallelFlux, which is a subset of Flux. In other words, it doesn't provide all the bells and whistles that Flux does, to give you a more concise way of processing multiple values in parallel. And the basic idea that you'll see here is you turn a Flux stream into a ParallelFlux, and then the computations can run in parallel on what are known as rails. Think of them as threads in a pool of threads. And then they run in somewhat of a round-robin manner on those rails doing the processing. When you're done with the parallel processing, you can then convert a ParallelFlux back to a good old sequential flux by calling the sequential factor method, which just returns it as a single thread. Very similar to Java parallel streams, where you can do everything in parallel. And just like for Java parallel streams, ParallelFluxes are intended for embarrassingly parallel tasks. Hopefully you remember what embarrassingly parallel means. It just means that there's no dependencies between the tasks. There's no need to communicate between the tasks. They can all run in parallel like a laundromat, and everything finishes when it finishes, and there's no need for sharing or communicating to get the work done. The other nice thing about ParallelFlux is it avoids that somewhat convoluted syntax of the flatMap concurrency idiom, so it's more direct. The way you make a flux into a ParallelFlux is by calling the parallel factor method. The way this works is it creates some rails, and the number of rails is dictated by the parameter that you pass in here. You can see that you can either give it the number of rails, like say 2, or you can just leave it with no parameters, in which case it'll pretty much default to the number of cores available on the processor. And then the elements that flow through the ParallelFlux will be processed by the rails, by the threads, in so-called round-robin order. You don't really have much control over how this works. It's just an implementation artifact you have to live with. By default, if you don't provide a parameter to parallel, the number of rails is set to the number of available CPU cores, which is pretty typical. You can change this setting programmatically by passing in a different value to parallel. Now, what's important to remember is that just because you make something be a ParallelFlux, it doesn't mean it's going to start running in parallel. So there's another step that you have to remember to do. So let's talk about some of these other operators. So there are a bunch of operators that can be used to process elements in parallel using a ParallelFlux. These are a subset of the overall Flux operators. There's a boatload of Flux operators. Remember, there's like several hundred Flux operators. There's only a handful in ParallelFlux, the ones that lend themselves nicely to the embarrassingly parallel processing semantics. And these include things like map, filter, concat map, flatMap, collect, and reduce. So it's some of the most important workhorse operators. you need to make sure you first call the runOn operator to specify where each of the rails will be used to observe the incoming elements. And runOn, as you can see here, takes a scheduler. So you have to give it a scheduler, and that scheduler, because of the fact it's done in round-robin fashion, there is no way to be able to do work stealing. So we've talked briefly about work stealing. Work stealing is something that comes with the Java Common Fork Join Pool and the Fork Join Pool framework, where it'll steal the threads that don't have anything to do, can steal work from other threads. That's not how the ParallelFlux works for whatever reason. And it returns a new ParallelFlux instance that can then do all this processing in parallel. Once the processing is done, once the parallel processing is done, then you typically need to convert the result back into a sequential flux, and that's primarily because a lot of operators that you might want only work on sequential fluxes, not parallel fluxes, because it's a subset of the total set of fluxes, of operators or methods that are defined on Flux. So ParallelFlux has a subset. The way this works is that when you call sequential, it'll merge the values from each of the rail in a round-robin fashion. And when you're all done, then you end up with a final result. So a common thing to do, not the only way to do it, but a common thing to do is to use the reduced method on ParallelFlux to be able to convert all the results that are being processed back into a mono by reducing it and doing some type of operation like adding or whatever to the elements as they're done. So here's reduce. It reduces all the values in a rail and across rails into a single sequential value, which comes back as a mono. And it's passed a by function that does this in a pairwise manner. What you get from reduce is a mono that will emit the reduced value, or if the ParallelFlux didn't have anything to do, it'll come back with an empty result. So you normally just get a single result back, which is what you might want here. So what happens, here's kind of an overall view of how this works. So we have a flux, we give it some input, in this case an array. We then make it a ParallelFlux. Then we say run on this scheduler, the parallel scheduler. It could be another scheduler, but it's the parallel scheduler here. Do the multiplications in different threads, reduce the results by adding them together, and then display the results if everything goes well. This is how we designate the scheduler to use. In this case, because everything is computation intensive, we use the parallel scheduler. But if you need to do for I/O, you would use a different type of scheduler, and we'll talk about that later. So that's the end of the overview of the ParallelFlux class. Very useful class if you have embarrassingly parallel processing to be done for your program.